Saturn's rings are disappearing, right now, today, as you watch this video. They're being pulled into Saturn's atmosphere by gravity, what scientists call ring rain, at a rate of roughly 10,000 kilograms per second. 10,000 kilograms every second. At that rate, the rings will be completely gone within 100 million years. That sounds like a long time, but the solar system is 4.5 billion years old. On that scale, 100 million years is nothing. We are catching Saturn in what may be the last 2% of its ringed existence. And here's what makes this genuinely unsettling. The rings aren't ancient, they're young. Astronomers now believe they formed somewhere between 10 and 400 million years ago, which means they appeared around the time dinosaurs were walking the Earth. Saturn didn't always look like Saturn, and soon, again, cosmically speaking, it won't look like this again. But the rings are only the beginning of what makes this planet strange. By the end of this video, I'll tell you about a discovery on one of Saturn's moons that has forced scientists to completely rewrite the rule book on where life can exist. Let's start. Saturn is the most beautiful planet in the solar system. Everyone agrees on that. The rings, the golden atmosphere, the perfect geometry of it all. When Galileo first saw Saturn through his telescope in 1610, he didn't understand what he was seeing. He thought it was 3 planets, a large one with 2 smaller ones on either side. His telescope wasn't powerful enough to resolve the rings. It took another 50 years and a better telescope before Christian Huygens figured it out. A ring, a single, thin, flat ring surrounding the planet, separate from it, not touching. The discovery stunned the scientific world. Nothing like it had ever been seen. Nothing like it exists anywhere else in the solar system with the same visual drama. But here's what Saturn has been hiding behind those rings. It is the least dense planet in the solar system. Its average density is 0.687 grams per cubic centimeter. Water has a density of 1.0, which means if you could find a bathtub large enough, Saturn would float. It has a storm at its north pole that is shaped like a perfect hexagon, 30,000 kilometers across, and has been stable for decades. Nothing in atmospheric physics fully explains why it's a hexagon. One of its moons shoots liquid water hundreds of kilometers into space. Another has a complete weather cycle, rain, rivers, lakes, and seas, but made entirely of liquid methane instead of water. And its rings, the most iconic feature in the entire solar system, are disappearing. Saturn is not what you think. Let's go beneath the beauty. Saturn is a gas giant, like Jupiter, but with crucial differences. Its mass is about 95 times that of Earth, but its volume is enormous. Roughly 764 Earths could fit inside. And most of that volume is almost nothing. Hydrogen and helium in their lowest density forms. At the cloud tops, you'd find ammonia ice crystals, similar to Jupiter. But Saturn's atmosphere is noticeably calmer than Jupiter's. The bands are more muted, the colors less saturated. Pale gold, cream, faint amber. Saturn looks quieter. It isn't. Wind speeds at Saturn's equator reach 1,800 kilometers per hour, nearly 5 times the speed of sound on Earth. The calmness is an illusion. The atmosphere is simply too thick and uniform to show the turbulence clearly from the outside. Below the cloud layers, the structure mirrors Jupiter, molecular hydrogen giving way to metallic hydrogen as the pressure climbs. But Saturn has less mass pressing down, so the metallic hydrogen zone begins deeper and is less extreme. At the very center, a rocky and icy core, estimated at 9 to 22 times the mass of Earth. And here's where Cassini changed everything we thought we understood. Using a technique called ring seismology, essentially listening to how Saturn's gravitational vibrations disturb the ring particles, the way seismologists listen to how earthquakes propagate through Earth. Scientists discovered that Saturn's core is not compact and solid. It is fuzzy, diffuse, extended, a soup of rock, ice, and hydrogen that gradually transitions into the surrounding gas without a clear boundary. The core of Saturn may extend 60% of the way to the surface. Sound familiar? Jupiter has the same thing, two gas giants, both with dissolved, diffuse, extended cores. Neither matching our previous models. The interiors of giant planets are telling us something about planetary formation that we clearly didn't understand before Cassini and Juno arrived. And we're still working out what that something is. But what makes Saturn truly unique in the solar system isn't its interior, it's what's around it. Saturn's rings are not solid. They look like flat disks from a distance. But they are made of billions of individual particles, chunks of water ice ranging from microscopic grains to house-sized boulders, all orbiting Saturn at different speeds in an almost perfectly flat plane. The ring system stretches about 282,000 kilometers from end to end, but its thickness? In most places, less than a kilometer. Some sections are only 10 meters thick. Think about that. A structure wider than the distance from Earth to the Moon, 10 meters thick. The proportional thinness of Saturn's rings, relative to their width, is greater than a sheet of paper, and they are not a single ring. The main rings, labeled A, B, C, and D from outside in, are separated by gaps. The largest gap, the Cassini division, is 4,800 kilometers wide. It looks empty. It isn't. It contains thin, dusty material. But it's dramatically less dense than the main rings because orbital resonance with the moon mimas has swept most particles out. Shepherd moons maintain the ring edges, tiny moons embedded within or just outside the rings, their gravity herding the ring particles into precise boundaries. The B ring alone contains more material than the moon mimas. The entire ring system contains enough mass to build a small moon. Now, where did they come from? For decades, scientists assumed the rings were ancient, formed at the same time as Saturn, 4.5 billion years ago. Cassini proved they are not. By measuring the rate at which the rings are absorbing dust from meteorite impacts, and comparing the current dust load to what it should be if the rings were ancient, scientists calculated the rings are between 10 and 400 million years ago. Young, cosmically brand new. The leading theory for their origin, a moon of Saturn, perhaps the size of Titan, drifted too close to Saturn due to gravitational interactions. It crossed what's called the Roche limit, the point at which tidal forces overcome the moon's own gravity. It was torn apart. The debris spread into a ring. A moon died to make the rings. And the rings are now dying in turn. Ring rain. The particles at the inner edge of the rings are electrically charged by ultraviolet radiation and the solar wind. That charge connects them to Saturn's magnetic field lines, which pull them down into the atmosphere. 10,000 kilograms of ring material per second raining into Saturn. At that rate, without replenishment, the rings will be gone within 100 million years. We are watching the rings of Saturn in their final era. The most iconic image in astronomy is temporary, and we happen to be alive to see it. At Saturn's North Pole, there is a storm. Not a circular storm, like the Great Red Spot on Jupiter, not a chaotic swirl of competing weather systems. A hexagon, a perfect six-sided geometric shape, each side measuring approximately 14,500 kilometers, larger than Earth's diameter. The entire hexagonal storm system rotates as a unit. It has been there since we first observed it with Voyager 2 in 1981. 40-plus years of observation, perfectly stable, perfectly hexagonal. How does a storm form a hexagon? In nature, in a gas giant atmosphere? The answer involves fluid dynamics. When a circular jet stream, a fast-moving wind current, encounters waves in a slower surrounding atmosphere, under the right conditions, the interaction can create polygon shapes. The number of sides depends on the wind speed ratio between the fast jet and the slower surrounding atmosphere. Scientists have reproduced hexagonal patterns in laboratory tanks of rotating fluid. The physics works. But why Saturn's polar jet produces a hexagon specifically, rather than a pentagon or an octagon, is still not fully constrained by the models. And then there's what's inside the hexagon. At the very center, a polar vortex, a circular storm at the eye of the hexagon, about 2,000 kilometers wide, with 150-meter-per-hour winds at its edge and a clear eye at the center, like a hurricane, but larger than the entire continental United States. The hexagon rotates around this central vortex. The vortex rotates inside the hexagon. Both maintain their structure indefinitely. Cassini photographed the hexagon in multiple wavelengths over years of continuous observation. And in 2018, something changed. Cassini's final images showed the hexagon had changed color. From the blue-gray it had appeared in earlier mission images, it had turned golden yellow. The cause: seasonal change. As Saturn moved through its 29-year orbit and the North Pole received more sunlight, photochemical reactions in the atmosphere changed the composition and color of the haze. Even the hexagon has seasons. A perfect geometric storm, big enough to swallow Earth, changing color with the Saturnian seasons. And still, nobody fully understands why it's a hexagon. In 2005, the Cassini spacecraft was flying past a tiny moon of Saturn, just 504 kilometers across, barely visible from Earth, when its instruments detected something extraordinary: water vapor and ice particles shooting out of the South Pole, geysers, on a moon of Saturn. The moon is Enceladus. And what Cassini found there, over the following decade of close observation, is arguably the most important discovery in the history of planetary exploration. Enceladus has a global subsurface ocean of liquid water beneath its icy shell. Not a theoretical inference, not an indirect measurement. Cassini flew directly through the plumes erupting from the South Pole, through the actual material coming out of the interior, and analyzed it directly. The results: water, salt, silica particles, indicating hydrothermal activity on the seafloor, organic molecules, molecular hydrogen, produced by the reaction between hot water and rock, carbon dioxide, methane. Every single one of those components, when found together in a liquid water environment, is associated on Earth with the conditions that support microbial life. Every single one. The silica particles were particularly significant. On Earth, silica particles of the specific size Cassini detected in the plumes only form in hydrothermal vent environments where water is heated to at least 90 degrees Celsius and interacts with silicate rock at high pressure. Enceladus has hydrothermal vents on its seafloor, hot water interacting with rock, in a liquid water ocean, under ice, on a moon of Saturn. 1.4 billion kilometers from the Sun. The tidal heating from Saturn, the same gravitational kneading that keeps Io volcanic, keeps Enceladus's ocean liquid and its vents active. And in 2023, a reanalysis of Cassini data found phosphorus in the plumes. Phosphorus, one of the 6 essential elements for life as we know it. The last of the 6 to be confirmed at Enceladus. All 6 chemical building blocks of life, confirmed in the plumes of a moon of Saturn. Enceladus is, as of right now, the most promising place to search for extraterrestrial life in the solar system. More promising than Mars, more accessible than Europa, because its ocean is actively venting material into space. We don't need to land and drill. We just need to fly through the plumes and catch what's already coming out. And that is exactly what the next mission will attempt. Titan is Saturn's largest moon, and it is, without question, the most Earth-like world in the solar system, other than Earth itself. It has a thick atmosphere, denser than Earth's, in fact. Surface pressure about 1.5 times greater than what we breathe. Nitrogen-dominated, just like Earth's. With an orange photochemical haze so thick that the Voyager probes couldn't see the surface at all. It has weather, real weather, clouds that form and dissipate, rain, seasons that change over its 29-year orbit of Saturn, wind-driven dunes covering vast equatorial regions. It has rivers, carved channels visible from orbit, their branching patterns unmistakable. These are drainage networks, formed by liquid flowing downhill over geological time. It has lakes and seas, collected at the poles. The largest, Kraken Mare, is larger than the Caspian Sea. Everything I've just described sounds like Earth, but none of it involves water. Titan is too cold for liquid water. Its surface temperature is minus 179 degrees Celsius. On Titan, water is rock, frozen solid, forming the bedrock of mountains and riverbeds. What flows on Titan is liquid methane and ethane. The rain is methane. The rivers are methane. The lakes and seas are liquid hydrocarbons. Titan has a complete methane cycle. Methane evaporates from the surface, rises into the atmosphere, condenses into clouds, rains back down, collects in lakes, flows through rivers to the seas. Exactly like Earth's water cycle, but with a completely different molecule. And beneath the surface, like Enceladus, there may be a subsurface liquid water ocean, kept warm by internal heat and tidal forces. So Titan potentially has 2 completely different environments where life might exist. On the surface, exotic chemistry in liquid methane, potentially supporting life forms with completely different biochemistry than anything on Earth. And underground, a liquid water ocean where conventional life as we know it might survive. 2 possible biospheres on a single moon. The Dragonfly mission, a nuclear-powered rotorcraft, will arrive on Titan in 2034. It will fly from location to location on Titan's surface. No rover could traverse the terrain, sampling different environments. River sediments, impact crater interiors where water ice and organic material were briefly mixed by the heat of impact. The organic dunes. If there is life on Titan, surface life, exotic life, Dragonfly will find its chemical fingerprints. On September 15, 2017, the Cassini spacecraft, after 13 years in orbit around Saturn, performed what NASA called the grand finale. Running low on fuel, with the mission coming to its end, the team made a deliberate choice. Rather than risk Cassini drifting and potentially contaminating Enceladus or Titan with Earth microbes, however unlikely, they plunged the spacecraft into Saturn's atmosphere. 22 times in its final months, Cassini dove between Saturn and its innermost ring, a gap less than 2,000 kilometers wide, a region no spacecraft had ever entered. And in those final dives, it made its most surprising discovery. The gap between Saturn and its rings is not empty. It contains complex organic molecules, not simple compounds. Complex, large organic molecules raining down from the rings into Saturn's atmosphere, or wafting up from the atmosphere into the ring region. The chemistry between Saturn and its rings is active, dynamic, molecules moving in both directions. This was the last thing Cassini sent home before it burned up in Saturn's atmosphere. A confirmation that the rings and the planet are chemically connected, that the boundary between planet and ring system is not a dead vacuum, but a chemically active exchange zone. We lost Cassini at 7:55 a.m. Pacific Time on September 15, 2017. The signal simply stopped. The spacecraft was gone, consumed by the planet it had spent 13 years studying. It left behind more than 600 gigabytes of scientific data that scientists are still analyzing today. Data that produced the Enceladus ocean discovery, the ring age calculation, the fuzzy core finding, the hexagon seasonal color change. And the data from those final grand finale dives is still being fully processed. Before 2035, the Dragonfly mission will land on Titan. An Enceladus orbiter and lander mission, currently in early planning at NASA and ESA, may follow in the late 2030s. The questions Cassini raised: can life exist in Enceladus's ocean? Can exotic life exist in Titan's methane seas? Will be answered within the lifetimes of most people watching this video. Saturn taught us that the most beautiful thing in the solar system is also one of the most scientifically consequential. That the rings we admired for 4 centuries are young and temporary. That its moons are more interesting than the planet itself. And that the boundary between life and no life may be much more flexible than we ever assumed. Cassini changed everything, and what comes next might change it again. Subscribe, hit the bell, and tell me in the comments, Enceladus or Titan? Which world do you think is more likely to have life? I genuinely don't know the answer, and I love that. Until the next mission.